So for my physics project, my first thought was to actually use an example of the fastest train in the world, but that was a little difficult to use. So I just used the example of a passenger train traveling from Shanghai to China, or to Shanghai, China to Nanjing, China, non-stop with a speed of 95 miles per hour over a distance of 190 miles. And that was representing constant velocity. The force diagram actually got kind of cut off here, but you can see that there's friction on the left of the train, and force of gravity shown below it, and above it would be the normal force. And so we have the position versus time graph, and instead of seconds I used hours. And so since it's at a constant velocity of 95 miles per hour over a distance of 190 miles, every hour the car reaches 95 more miles every hour the car reaches 95 more miles is what is represented in the position versus time graph. And the slope is actually shown in tiny print there. I used Logger Pro to make my graphs just to seem a little more accurate. And you can see that the slope is 95 miles per hour, since the constant velocity is 95 miles per hour. And you can see at half an hour the slope is, let's see, it's kind of hard to see. So you can see at 1 hour it's at 95 miles, and then at 2 it's kind of cut off here, but it would be 190, somewhere there. And you can see that it's pinpointed at 49.5, since or about 49, because it's supposed to be half of 95. And this is your velocity versus time graph, in which velocity is constant at 95 miles per hour. And you know that the area of your velocity versus time graph is also your change in position or displacement, which you can get from multiplying the time by the velocity. And then from that velocity versus time graph, you can get acceleration using the slope of that. So the slope is 0, right there. So the acceleration would be 0. And it's explained by an equation known as sigma f, or sum of all the forces equals mass times acceleration. Yeah. And then, sorry, I couldn't get a clear view of the entire project because it was 2 feet by 3 feet, so it was a little hard to get. So now I'm going to continue on to constant acceleration. And I have a 4 kilogram box being pushed across a rough surface with friction and moves at a constant acceleration of 3 meters per second, or 3 meters per second squared. And the forces acting upon this box would be the kinetic force, and then to the right of it would be the tension or the force of the person. Below it would be gravity, and above it would be the normal force. And the net force diagram is shown next to it, with the force of the person on the top and then the normal force on the left, and then the weight on the right. And since it does have acceleration, these vectors may not equal to, or actually cannot equal to 0. Therefore, the sum of the forces and the friction must be opposite one another. Now, the position versus time graph is shown here with the slope being 3 meters per second. So we have 3 here, 3 at 1 second, 6 meters at 2 seconds, and 9 meters at 3 seconds. Pretty clear. So every second the car travels 3 more meters. And the area of this velocity versus time graph, I told you, is equal to displacement. And, oh, I forgot to mention, I know my position versus time graph is off because the constant acceleration does not, the graph, position versus time graph for the constant acceleration does not resemble the position versus time graph for constant velocity because it's not just going in a slope, it's actually in a curve. So that's one thing I did wrong. I also mentioned the slope of the velocity versus time graph equals acceleration, which is 3 over 1 here, which is 3 meters per second squared. And that's the acceleration. Now for the bottom, I had to mention some aspects of force and Newton's second law. So yeah, here's where I started. Newton's second law was net force equals mass times acceleration. Newton's third law is for every action there's just lost it. There's an equal and opposite reaction, and the size of the forces on the first object equals the size of the force on the second object. So the forces are actually symmetrical if they were to be graphed, and that's why the force equals half of an interaction. I think that was right. Yeah, okay. Yeah, but that's the idea of it. Okay.